Okay, so let's get into chapter 15, which deals with the topic of solutions. All right, so what do we mean by solutions? Well, a solution is basically a homogeneous mixture of two or more substances. So basically, it's a situation where you have one substance or more than one substances um, dissolved or added to another substance and they all mix completely. All right. Now, solutions are made up of two parts. You have the solute and the solvent. Now, to a large extent, what is determined to be the solute or solvent is dependent on which one is in greater abundance. All right. Especially if both components are in the same phase. If they're in different phases, then it's a bit different in terms of the definition of solute and solvent. So as you can see on the screen, it says here that a solute is a component that is dissolved or is the least abundant component of the solution. The solvent, on the other hand, is a dissolving agent, and it is the one that is in the most abundance of the different components in a mixture. So here are the common types of solutions. You can have two substances that are gases that are completely mixed. That is a solution. Now, which one is a solvent and which is a solute is dependent on which one is in greater amount. So, for example, the air we breathe is a solution. It's a mixture of gases. The majority component of that mixture is nitrogen, and therefore nitrogen would be the solvent, and all the other components, oxygen, carbon dioxide, etc., all those other components would be solutes. Now, if you have a gas dissolved in a liquid, then the gas is considered to be the solute and the liquid is considered to be the solvent. A good example of this is the carbonated beverages or soft drinks, which is basically carbon dioxide dissolved in water. Of course, you have other things like flavors and so on, but that's basically what that solution is. So if you have a gas dissolved in a liquid, the gas is a solute and the solvent would be the liquid. If you have two liquids mixing, then the liquid in greater amount would be the solvent. All right, and there are several examples we can point to of that. For example, antifreeze. Antifreeze is largely a mixture of a compound known as glycol dissolved in water. So water would be the solvent in that case, and the glycol, which is a liquid, would be the solute in that case because water is in greater amount. And then you can have the situation of a solid dissolved in liquid. The solid would be the solute, the liquid would be the solvent. A water solution, or a salt solution I should say, would be a good example of this. Now, believe it or not, you can also have a gas dissolved in a solid. A good example of this is hydrogen. It is possible to dissolve hydrogen in the metal platinum. That is also a solution where the gas is a solute and the solid would be the solvent. And then finally, you can have solid dissolved in a solid. These are known as alloys, such as brass. And again, as in the case of gas-gas and liquid-liquid mixtures, the one in greater amounts would be the solvent, while the other components would be the solute. Okay, so let's talk about the properties of solutions. As we said before, it's a mixture of two or more substances, which is homogeneous and has a variable composition. And what that means is that the ratio of the solvent to solute can be varied. So there's literally an infinite number of possibilities in terms of the proportions of the solute to solvent in any mixture. In terms of what happens at the microscopic level, the solute is molecular or ionic in terms of its size, and solutions are either colored or colorless and are usually transparent. So usually, if it's not transparent, it's not a solution. More than likely what you have are particles that are not of the microscopic level that are basically suspended in a mixture. So in that case, it would not be a solution. The solute, of course, in a solution would be uniformly distributed through the solution and will not settle out. That's one big difference between a solution and a suspension. It is very easy, relatively speaking, of course, to separate a solute from the solvent. It can be done by physical means, I would say that the most common physical mean is evaporation, but there are others as well. The solute particles, of course, of a solution, they are either molecular or ionic. So we're talking about particle size ranges from 0.1 nanometers to 1 nanometers. So those are basically the characteristics associated with solutions. So this is what happens when a solution is formed. You have your solvent, you have your solute, and you add your solute to your solvent, and the resulting combination will be your solution. All right? Okay, let's talk about this term solubility. Solubility is a term that we refer to the extent to which a solute will dissolve in a specified amount of solvent. And there are different ways and units that are used to express solubility. You can express, for example, the solubility in terms of grams of solute per 100 grams of water. And this is a table showing you the solubility of different substances in water at 20 degrees and at 50 degrees, right? So as you can see here, for example, sodium chloride has a solubility of 36 grams per 100 grams of water. Potassium chloride at 20 degrees is slightly less soluble. Sodium nitrate is more soluble to a great extent than either sodium chloride or potassium chloride, and so on and so forth. And as you can see, the solubility is dependent on temperature. So for example, the solubility of sodium chloride at 20 degrees is 36 grams per 100 grams of water. It increases slightly to 37 degrees per 37 grams, I should say, per 100 grams of water. But of course, you can have other situations where the solubility increases drastically, as in the case of, let's say, silver nitrate. Its solubility at 20 degrees is 2 to 2.0 grams per 100 grams of water, and then it's more than doubled when you increase the temperature to 50 degrees. All right, so this is one factor we're going to look at, how temperature affects the solubility. We're going to look at that shortly. Terms that are oftentimes used to describe the solubility of a solute in a solvent. These terms here, we say usually very soluble or moderately soluble or slightly soluble, or to the other extreme, totally insoluble. All right. So most substances that are added to a potential solvent, the resulting mixture can be described by any one of these terms. All right. In terms of terms that we use to describe the solubility of liquids, there are two main terms. You have miscible and immiscible. So when we say a liquid mixture is miscible, we're talking that those components that make up the liquids in that mixture would be completely homogeneous. They're completely mixed with each other. A good example of this is methyl alcohol and water, right? Methyl alcohol and water are soluble in each other in all proportions. Doesn't matter if it's a 90% water, 10% methyl alcohol, or the other way around, or 50-50 or 75-25. It doesn't matter. They will completely mix, right? A mixture that is immiscible are basically liquids that would simply not mix. So when you add them to each other, they end up forming two layers. A good example of this would be oil and water, or gasoline and water, right? If you add gasoline to water, you'll form two layers. The gasoline will be at the top, the water will be at the bottom. It doesn't matter if you shake it up to try to mix it. Once you leave it to stand, it will simply settle out into two layers. Okay, so there are some ionic compounds that are more soluble than others in water. And this chart here basically is a guideline for predicting the solubility of ionic compounds. There's a better one that I've posted in Canvas, of course, in that packet that you'll have available. So you can refer to that. That's a better table. We have actually used that table before when we were doing the topic of balancing net ionic equations, right? So you may want to remind yourself of what is in that table. Okay, so we're going to stop here. The next video will deal with the factors related to solubility. Until next time.